Hello and welcome to another read-along of College Geometry, a problem-solving approach. Today we are beginning Chapter 2 on geometric shapes and measurement. Geometers used informal reasoning until approximately 300 BC when Euclid wrote his famous set of books called The Elements. In The Elements, Euclid made two very important contributions to the way we study mathematics. First, he organized existing results in a manner that linked them together. In this way, we can verify or prove later results using earlier results. Second, Euclid introduced us to an axiomatic system. Put that in blue. All right. It was built upon common notions, definitions, postulates, axioms, and theorems. Later, mathematicians replaced some of Euclid's definitions with undefined terms to form what is now known as an axiomatic system. So you can see a visual representation of the system, and all it means is that our entire knowledge of mathematics is built in layers, one thing built on top of another, and you have to start somewhere with the undefined terms. That is the essence of the axiomatic system, most commonly made explicit in geometry, but it does apply to almost all mathematical disciplines. Our new strategy for this chapter is look for a formula, which you can think of that really as a combination of using a variable and look for a pattern, so it's kind of a two-for-one deal. So here's a problem to get you started with looking for a formula. Find the number of squares of all sizes in the 10 by 10 grid of squares shown. To find the total number of squares, you must count the number of different 1 by 1 squares, the 2 by 2 squares, etc., etc. It's going to be a lot of squares. Right. In general, clues for when looking for a formula may be appropriate. A problem suggests a pattern that can be generalized. Okay, so again, that finding a pattern and generalization. Ideas such as distance, area, volume, or other measurable attributes are involved. Applications in science, business, and so on are involved, so that application feature, very good formula. Right? A problem requires counting a number of possibilities. Okay, you can count them by hand, or you can look for a formula. And we will get to the solution to this initial problem at the end of the chapter, which is not going to be this video. All right. One investigation you can do to get into geometry is this estimation and measurement golf game, which requires you to literally estimate as you go along. To summarize those rules shown above, you will print out this page, and you will estimate where from the golf tee to the hole, how far is that total distance, how many centimeters from here to there, and about what degree angle, if the horizontal is 0 degrees, from there rotated up, this is what, well, totally vertical would be 90, so this is somewhere in between, about how many degrees from here to there. Okay? And you'll do that for each of the 3 holes in order, estimating their distance and degree, and then you actually measure it. You get a ruler and a protractor, and you measure, and you see how close you were, okay? And you'll keep track of that. And you can add up your strokes and penalties and give yourself a kind of a golf score. So that's a little fun one. You can go ahead and freeze, pause there, take a screenshot, print that out, and play with that at your leisure. All right, to introduce the chapter properly. Geometry itself was initially used to solve problems involving measurements on the earth. Geo means earth, and metry means measure. So it's literally earth measure. Although the earth is essentially spherical in shape, when we view the earth in small regions, it appears to be flat. Okay, just look at any, floor of any building. Okay? Even though if we added together all the floors of all the buildings, we would eventually get a curve around the Earth. The difference is scale. So thus, in many practical situations involving measurement, a small portion of the surface of the Earth is assumed to be flat and considered to be part of a plane. There's that geometry term. This is one of the reasons plane geometry has been a main focus of school mathematics for the past several centuries, because every building we build is built upon a flat, level, plane surface. In Chapter 1, we solved problems related to geometry by reasoning informally. In this chapter, we begin to formalize the study of geometry in the spirit of Euclid. A modern axiomatic system begins with a small set of undefined terms and builds through the addition of definitions and postulates to the point where many rich mathematical theorems can be proved. Okay, that is all good stuff there. Add that to your vocab list, and note we've got axiomatic system itself. Let's go a little bit thicker pen here. Definitions, postulates, and theorems, right? There you have it visually in the figure. In section 2.1, that's this video, we introduce some undefined terms and postulates and many definitions of plane geometry. Then we study common two-dimensional geometric shapes in section 2.2. Section 2.3, we look at angle measures in polygons and how we can arrange polygons to cover a plane. Oh, that's a fun one. In section 2.4, we examine three-dimensional shapes. Finally, in section 2.5, we introduce dimensional analysis, a useful technique for solving problems involving units of measure. Spoiler alert, every practical application of mathematics, and specifically geometry, will require the involving units of measure. All right, so section 2.1 proper. Here we go. The undefined terms, definitions, postulates, and introduction to segments and angles. So a problem to get us thinking about this is the compass card, or compass rose, marked with the 32 equally spaced points of the compass used for navigation. An example with some of the directions labeled is shown. You got your north, your east, your northeast. Between north and northeast, we have north by northeast. If a ship sailing west by northwest changes its course to northeast, it has turned through an angle of how many degrees? From west, northwest, so from here to northeast. So what is the angle between those directions? We'll come back to that at the end. So elements of an axiomatic system. How does this work? Definitions, as they appear in dictionaries, are circular. That is, if you continue to look up key words in a definition, you will likely revisit one of the words you have found already. All right? I imagine you've probably come across this before, but every word you look up, if you look up the word definition, well, there would be other words in there that if you assume you don't know those, you have to search those up. Eventually, they all come back to themselves, right? Every word builds upon the definition of another word. By contrast, in an axiomatic system, we agree to leave some terms undefined and then build definitions of other terms and postulates from those undefined terms. The undefined terms can be described but cannot be given precise definitions using simpler known terms. Okay? And there's a whole branch of philosophy that gets into this, but the idea of you can only get so simple. Well, think scientifically, right? The atom used to be considered the smallest possible particle, right? And as far as certain properties apply, it still is, but we found now that there are things inside the parts of the atom, right? And we found further there's things inside of those things that make them up, right? There's always a smaller and smaller piece. The axiomatic system sets up a few undefined terms that we've established from the beginning. We are not going to reduce these any further. These are as simple as it gets. The three undefined terms in geometry are point, line, and plane. We think of a point as a circular dot that is shrunk until it has no size. Okay? A dot that has no size. By a line, we can think of a wire of points stretched as tightly as possible, and hence straight, of infinite length denoted by the arrowheads, and having no thickness. So a line, a wire of points stretched tightly as possible, of infinite length, having no thickness. And finally, we can think of a plane as a sheet of paper of points with no thickness, stretched tightly, extending infinitely in all directions. Okay? No thickness, stretched tightly, extending infinitely in all directions. These descriptions provide a way for us to visualize points, lines, and planes, but they are not definitions. Okay? We define space to be the set of all points. Any collection of points is called a geometric figure. Okay? So now we're getting into these are definitions, right? Space is a definition that builds on points. But what are points? Well, there's these things that you just have to accept exist. So space is the set of all points. Any collection of points is called a geometric figure. In particular, lines and planes are composed of points and hence are geometric figures. See, we have there, we've taken a dot down as small as possible to achieve the true point, line extending in both directions, and a plane extending in all directions within the bounds of 2 dimensions. Okay. Now, postulates are statements that we assume to be true. They're kind of like the undefined terms, a little bit different. Postulates state relationships among defined and undefined terms. Include that in your definition of postulates. Okay? The purpose of stating postulates is to establish some first principles upon which a geometry is based. This technique of developing a system, such as geometry, by beginning with a few first principles, was perhaps the most significant achievement attributed to Euclid. After introducing postulates and some definitions, we may deduce new results using that deductive reasoning. Results that we deduce from undefined terms, definitions, or postulates, and or results that follow from them are commonly called theorems. Okay? So notice that. Theorems are merely results that have been deduced from prior results or prior definitions, postulates, and the undefined terms. They are in no way related to the general populace use of the term theory, which is to say something you think is true but are unsure of. Okay? A true mathematical theorem we are very sure of. Now, some actual relationships among the points, lines, and planes. Now we begin to examine some of the postulates of geometry that will be assumed in this book. And assuming is not a bad thing here. It means this is so simple, we cannot prove it with other prior simpler things, because this is the simplest relationship we can establish at the beginning. So, postulate 2.1. Every line contains at least 2 distinct points. When a line contains a point, we say that the point is on the line. Lines are named by any 2 of their points together with a double arrow over the letters. For example, line AB or line BA is shown in figure 2.4. We have right here. So all of these, I could put more points on the line. I have decided to label these ones and give it a name. Right. A line may also be named by a single lowercase letter. For example, line AB in figure 2.4 can be called line L, as we've shown off to the side there. Although the preceding postulate states that any line contains at least 2 points, in fact, we will see that a line contains infinitely many points. This result follows from a postulate to be stated soon. As you may remember from your experience with graphing lines in algebra, 2 points determine a unique line. You recall the point-slope form of a line. The next postulate formalizes this idea. Postulate 2.2. 2 lines are contained in one and only one line. Sorry, 2 points contained in one and only one line. Postulate 2.2 suggests that all lines are, quote, straight, unquote, because otherwise more than one line could be drawn through 2 points. So we have this guy right here. We have the single line AB, and if you were to draw anything else, any other curve, any other shape, whatever you want to call it, something that goes through and contains A and B, you cannot call that a line. All right. Also, because we can imagine 2 points arbitrarily far apart, this postulate suggests that lines are infinite in length, because all you have to do is start with 2 points that are infinitely far away. The next postulate, as illustrated in figure 2.6, suggests a connection between the straightness of lines and the flatness of planes. That is, just as lines are straight, planes must be flat. Postulate 2.3. If 2 points are in a plane, then the line containing these points, remember, 2 points defines a line, the line containing these points is also in the plane. Okay? So within this sheet of paper here, we have line AB, and if you were to draw some other curve, this is something that's going, right? Within this sheet of paper, you have a line drawn there. Imagine trying to take some other curve that goes up, over, and through, back down, right, into that third dimension through the page to connect those points. That is A, not a line, and B, not part of the plane. So this helps define the plane as being flat. Points are considered to be collinear if there is a line containing all the points. Here we go. And non-collinear if there is no line that contains all of the points. So these are grouping terms. Okay? These are terms that refer to various groups of points. Figure 2.7, A, B, and C are collinear. A, B, C is there. A, B, and D are non-collinear. Okay, if you were to make the group of just A, B, and D, the whole group is non-collinear because they do not lie on one line. Just as 2 points determine a unique line, 3 non-collinear points determine a unique plane. The next postulate states this fact. Postulate 2.4, 3 non-collinear points are contained in one and only one plane, and every plane containing at least 3 non-collinear points. We have any plane here automatically contains at least 3 points, and any 3 points defines the plane. Postulate 2.4 guarantees that a plane consists of more than a single line, because we have more than 2 points. Points are called coplanar if there is a plane containing all of the points, and are said to be non-coplanar if there is no plane that contains all of the points. So coplanar and non-coplanar work exactly like collinear and non-collinear. In figure 2.8, for example, D is above the plane containing A, B, and C. There it is, floating out there in space. So points A, B, and C are coplanar, whereas A, B, C, and D are non-coplanar. The next postulate makes a similar statement about space. Postulate 2.5, in space, there exist at least 4 points that are not all coplanar. Postulate 2.5 assures us that space is not just a single plane, that is, space is at least 3-dimensional. Right. And that is the extent you could, in theory, continue such a pattern to create 5 dimensions, 6 dimensions, 7 dimensions, and so on, but we're going to stop at 3. All right, line segments and their measure. The next postulate involves the real number line and is one that will allow us to draw many conclusions about plane geometry, as well as allow us to find lengths of line segments. That is the ruler postulate. Notice that this one gets a unique name, not just postulate 2.6. Every line can be made into an exact copy of the real number line using a one-to-one correspondence. What does that mean? Well, take a look. Figure 2.9a shows a line L. There it is. 2.9b shows L labeled as a real number line using the ruler postulate. We have created a copy of the real number line. The real number associated with a point on a line is called the coordinate of that point. Right? The number associated with a point on a line is its coordinate. So for example, in 2.9b, the coordinate of point A here is -2. Only integers are labeled in figure 2.9b because it is impossible to label all the real numbers, every single fraction in between. Because the set of real numbers is infinite, postulate 2.6 implies that every line has infinitely many points. We were referencing that fact earlier. Also, because the real number line is infinite in length, this postulate implies that all lines are infinite in length. So now we have taken numbers from arithmetic and algebra and brought them directly into geometry. We measure distances between points using the coordinates of the points. We define the distance from A to B as the non-negative difference between their coordinates. Okay? So we've defined distance as a difference between coordinates, a non-negative difference. Figure 210, the distance from A to B is 3 minus -2 equals 5. So here we have it, here at -2, they're at 3, total distance between them of 5. The ruler postulate also allows us to define a line segment, as well as to find its length. If A and B are 2 points on a line L, then the line segment determined by A and B, written segment AB or segment BA, is points A and B together with all points on the line whose coordinates are between those of A and B. Okay? Line segment determined by A and B is points A and B with all the points in between. Points A and B are then called endpoints of segment AB. The length of the line segment AB, written as AB, so notice we drop the little bar over top, is the distance from A to B. In figure 210, AB equals 5. Because this AB is taken directly from here, so it has the same length of 5 units. Now, two segments are said to be congruent if they have the same length. When the segment AB and segment CD are congruent, we write segment AB is congruent to segment CD, which is read, as I just said, AB is congruent to CD. Or we write AB equals CD to mean the distance from A to B equals the distance from C to D. Okay? So this is saying the segments themselves are congruent, the lengths of the segments or the distances between their endpoints are equal because the distance represents a number. We indicate congruent line segments using marks as illustrated in figure 212. Okay? So here we have these segments and we put a small mark in between them. If more than one pair of segments is congruent, we use double or even triple marks. Or you could go quadruple if necessary, right? Just as long as the correspondingly congruent segments each have matching marks. Notice that because this has 2 marks, this has 1 mark, we in no way are implying that CD is congruent to EF. A portion of a line that has one endpoint and extends indefinitely in one direction is called a ray, as we've shown here, one endpoint and one arrow. More precisely, if points A and B are on line L, then ray AB, notice the symbol there, one endpoint, one arrow, consists of the points A and B and all points X on L whose coordinates satisfy one of the following. Gets a bit technical here. Either, 1, the coordinates of X is between the coordinates of A and B, so that covers the segment portion here. Or 2, the coordinate of B is between the coordinates of A and X. Right? So some X out there on the line such that now B is the one in the middle. Or we could have some X in here, but notice we cannot have an X out there because neither X is in the middle nor is B in the middle. That will not be part of the ray. All right, and finally we have angles and their measure. In addition to measuring lengths, it is important to be able to measure regions such as plots of land or walls of a building, right? The most practical direct application of geometry. Such regions are often bound by shapes composed of line segments. Here's a few. The sides of these shapes meet to form corners of various sizes. Two line segments or rays meeting at a common endpoint form an angle. So there we have the true definition of an angle, right? Two lines or rays meeting at a common endpoint. The common endpoint is called the vertex, plural vertices, of the angle, and the segments or rays are called the sides of the angle. Angles are usually named using the angle symbol, seen here, and 3 points. A point on one side, then the vertex, then a point on the other side. That order is important. So figure 215 here shows angle ABC, or you could call it angle CBA, going backwards, but notice in either case, B, the vertex, is still in the middle. And angle DEF or angle FED. Here. Points B and E are the vertices of angle ABC and angle DEF, respectively. Rays BA and BC are the sides of angle ABC, and segment ED and segment EF are the sides of angle DEF. So notice we can have our angle made of true rays that go on forever or merely segments. When the meaning is clear, we may name an angle using the letter at its vertex, a single letter at a time. For example, angle ABC may be called angle B. We may also name angles by numbers, lowercase letters, or Greek letters, as illustrated in 215b. Okay? So those indicators would be on the inside of the angle here. So we have angle 1, here is angle A, and here is angle theta. Angles are usually measured in terms of degrees or radians. In this book, we will usually use degree measure. If you go on to Algebra 2, Pre-Calc, and Calculus, they will transition over to using radians for most angle measures. If two rays coincide, such as ray AB and ray AC from figure 216, shown here, ray AB and ray BC, hey, they're right on top of each other. The angle they form has a measure of 0 degrees. So we can almost define 0 degrees. If ray AC is rotated counterclockwise one complete revolution, as shown in 117, so we've taken this up and we have, let's see if I can actually do this here, right? Spun it around, all the way, one complete revolution, as shown in 217, until it coincides with ray AB again, we say that the measure of this angle is 360 degrees. Okay, we have set that number. It is, yes, technically arbitrary. There are some historical reasons why we use that number in particular, but it's a very convenient number. The measure of an angle that is 1/360th of a complete revolution is 1 degree, written 1 degree sign. Okay? That is the definition of a degree. Degrees are represented by the small raised circle. Angles can be measured using a protractor, such as the one shown in figure 218, together with the following postulate. So let's take a look there, the protractor and its postulate. If we place one ray of an angle at 0 degrees on a protractor, and we place the vertex at the midpoint of the bottom edge, down here, so we have one ray down here, the vertex here, then there is a one-to-one correspondence between all other rays that can serve as the second side of the angle and the real numbers between 0 and 180 degrees inclusive, as indicated by a protractor. If you're feeling ambitious, you can also find a 360-degree protractor and go all the way around the circle that way. So, if we place the vertex of an angle at the center of the bottom of the protractor, right here at B, and we place one ray or segment of an angle at 0 degrees at either end of the protractor, okay? Either end. Notice there are two sets of numbers, one going from this side, 10, 20, 30, and the other on this side, inside the circle, 10, 20, 30. Then the measure of the angle is given by the number that falls on the other ray or segment. We use the inner numbers on the protractor for angles measured counterclockwise from the right, and we use the outer numbers for angles measured clockwise from the left. Okay? So it depends on where your angle is located. You can use either side, depending on which side lines up with and is most convenient to use. For example, in figure 218, the measure of angle ABC, so A starts here, B is our vertex, and then C, okay? Because A started on this side, we have to use the scale that starts at 0 on A. So that'll be the inside track, which gives us 30 degrees at segment C. So angle ABC is 30 degrees, written as measure of angle ABC equals 30 degrees. Or angle ABC equals 30 degrees, so long as the context is clear. The measure of angle ABD, ABD now up here, is 120 degrees. Do not be confused by this 60. We're starting at A, so we still have to start with the 0 on A and use the inside track. And the measure of angle EBC is 150. So E now on the other side, EBC, using the outside track. Because the measure of angle ABC is less than 90, it is an example of what is called an acute angle. On the other hand, angle ABD, whose measure is greater than 90 but less than 180, is an example of an obtuse angle. In fact, there are 5 special classes of angles. They are defined next and illustrated in figure 219. So you can put this whole box of definitions into your notes, right? So acute is between 0 and 90. You cannot have less than 0. Right angle is exactly 90. Obtuse is between 90 and 180. Straight angle is exactly 180. And a reflex angle is between 180 and 360. It's where you seem to be measuring the outside of an angle. Note, unless an arrow is included as shown in the reflex angle, we will assume an angle is not a reflex angle. So by default, we're always looking at the inside, the smaller of the options, unless the arrow indicates otherwise. Notice that in figure 219, a right angle is indicated by the square corner, right here, placed in the right angle. This is to indicate that we are, in fact, purposely making sure this is exactly 90 degrees and not drawing something that looks almost but is only 89. Two lines that form a right angle are said to be perpendicular. If lines L and M are perpendicular, we write L is perpendicular to M, and we use this upside down T symbol there. Two angles that have the same measure are said to be congruent. There's that word again. It can also apply to angles. We designate congruent angles using one or more small arcs, just like these small ticks on the line segments. You can use these small arcs inside the angle there. In figure 220, angle ABC is congruent to angle DEF. When two angles are congruent, as in this case, we write angle ABC is congruent to angle DEF, or using the shorthand names, angle B is congruent to angle E, indicated just with the vertex there. When the context is clear, we may also write angle B equals angle E to indicate that the two angles have the same measure. Or properly, you would write the measure. You would add a little M inside here. Right? The measure of angle B is equal to the measure. Shapes are congruent, measures and numbers are equal. Two angles whose sum is 90 degrees are said to be complementary. Very handy term. Two angles whose sum is 180 is said to be supplementary. For example, in figure 221, shown here, angle CBD and angle BDC are complementary because 34 plus 56 equals 90 degrees. And angle ABC and angle CBD, ABC, so this one out here, and DBC inside here, are supplementary because 146 plus 34 equals 180 degrees. Angles ABC and angle CBD in figure 221 are a pair of adjacent angles. In general, two angles, angle ABC and angle CBD, are said to be adjacent if they have a common vertex, B, and a common side. In this case, BC, and let's go ahead and highlight that. Adjacent if they have a common vertex and a common side. And if BC is between segment BA and BD, that is, the sum of the measures of angle ABC and CBD must equal the measure of angle ABD. Okay? In figure 222, shown here, angle POQ, and angle QOR, are adjacent angles. The angles POR and angle QOR are not adjacent. POR and QOR are not adjacent angles because the common side, OR, is not between OP and OQ, right? So it is important that whatever that, they have to have a common side that is between the other two sides. Common side is the one in the middle. They're not just overlapping. All right. In figure 23, we have CG is perpendicular to GE, as indicated by the right angle there. We have angle AGB equals 77 degrees. And angle CGD here, equals 54 degrees. And angle FGC equals 157. Use this information to do the following. Determine the measure of angle DGE, right here, BGC, AGF, and angle FGE, so all of the remaining unlabeled angles. Name one pair of complementary angles. Name 4 pairs of supplementary angles. And name 4 pairs of adjacent angles. Go ahead and pause the video here and give that an example a try. Okay, now that you are back, let's look at the solutions. First, finding angle DGE. So because CG is perpendicular to GE, right, we know that CGE, that whole angle there, is 90 degrees. In addition, angle CGD, this one here, plus angle DGE will equal angle CGE, right? We can get that from looking at it, that these two will combine to form the larger one. So we know that 54 plus our missing angle DGE must be equal to 90 degrees, or DGE is equal to 90 degrees minus 54 degrees, which is 36 degrees. To find BGC, which is here, we know AGD is a straight angle. We can see that from the diagram. And we know that AGB plus the BGC plus CGD all together form that straight angle, or 180 degrees. So fill in what we know, 77 plus the unknown plus 54 is 180. Combine, subtract these from both sides, and BGC is 180 minus 131, or 49 degrees. To find angle AGF, AGF is now down here. Because FGC was given as 157, we know the following. AGF plus AGB plus BGC all together make that 157 degrees. So we know our missing angle AGF plus 77 degrees plus 49 degrees must be the 157. Subtract, solve, AGF equals 157 minus 126, or 31 degrees. And finally, to find angle FGE, because the sum of the measures of all 6 non-overlapping angles is 360 degrees, we can find the measure of the remaining angle by subtracting from 360. So you take 360 minus the known 77, 49, 54, and the 36 and 31 that we just found to get 113 left. So now, the complementary angles are angles whose sum is the sum of whose measures is 90 degrees. Yep, that checks out. Because angle CGE equals 90, angle CGD and DGE are complementary. It's the only one on the diagram. Supplementary angles are angles, the sum of whose measure is 180 degrees. Because angle AGD is 180, we can say that the following pairs of angles are supplementary. AGB and BGD, AGC and CGD, AGF and FGD, and angle AGE and angle EGD. You can also look to the diagram to find whichever pair, this one plus this one, or this one and this one, right? Any pairing that forms this full straight line. And finally, adjacent angles share a common side and vertex but do not overlap. 4 examples of adjacent angle in the figure are angle AGB and angle BGC, angle BGC and CGD, AGE and angle EGC, and angle EGF and FGC. There are many other pairs that could also have been listed. All the pairs of angles in part C are also adjacent, right? So all of these supplementary ones are also adjacent. And finally, we come to a practical application of angles and angle measures. In surveying, navigation, and other applications of angle measure, we must often measure angles more precisely than to the nearest degree. In those cases, we may measure angles to the nearest tenth or hundredth of a degree, or in minutes and seconds, where 60 minutes equals 1 degree and 60 seconds equals 1 minute. If you are not familiar with that system, make note of it there. It is exactly as you'd expect the terms minutes and seconds based on time of day from a clock. We denote minutes using a single tick mark, for example, 45 equals 45 minutes, and seconds by a double tick mark. So, for example, 45 equals 45 seconds. So we might write an angle measure as 32 degrees, 15 minutes, 40 seconds. We could also write this same angle measure as 32 degrees plus a decimal fraction of a degree, as the next example shows. This will convert from one system to the other. Oops, let's not show off the solution just yet. Express the angle measure 32 degrees, 15 minutes, 40 seconds in degree plus a decimal fraction of a degree, round to the nearest thousandth of a degree. And then express the angle measure 75.3 degrees in degrees and minutes. Go ahead and pause the video here and try that out for yourself. And now that you're back, let's take a look at the solution. So we first consider how to convert 15 minutes to a decimal part of a degree. The 32 is already fine. Because we know that 60 minutes equals 1 degree, we know that each minute is 1/60th of a degree. So thus 15 minutes equals 15/60th of a degree. As you convert 40 seconds to a decimal part of a degree, remember that 60 seconds equals 1 minute. So 1 second equals 1/60th of a minute, or equals 1/60th of a 60th, or 1/3600th of a degree. Thus, 40 seconds is equal to 40 over 3,600 of a degree. Now we can perform the necessary conversion. So we turn this minute and second format now into fractions of degrees, which can then be converted into decimals. Right? You can feel free to run this division by hand or use a calculator. 15 divided by 60 is 0.25, and 40 divided by 3,600 is 0.011. So we get 32.261 degrees. And for part B, because 1 degree equals 60 minutes, we know that 0.3 degrees equals 0.3 times 60 minutes, which is about 18 minutes, right? 0.3 times 60. Thus, an angle measure of 75.3 degrees is equivalent to 75 degrees, 18 minutes. Going in this direction, I feel, is a little bit easier. And finally, we have the solution to our problem from the beginning. Remember the compass rose. Because there are 32 equally spaced directions on the compass card shown, the points are 360 degrees divided by 32, or 11.25 degrees apart. Therefore, the angle from west by northwest to north, from here to there, is 6 of those segments, 6 times 11.25, or 67.5 degrees. And the angle from north to northeast is 4 of those segments, 4 times 11.25 equals 45 degrees. Thus, the ship has turned through an angle of 67.5 plus 45 equals 112.5 degrees. And to wrap up, a reminder that geometry is all around us. Cameras and artists' canvases are often set upon some form of tripod. One explanation for the use of a tripod is that 3 points determine one and only one plane. This means that a 3-legged stand will be more stable than one with 4 or more legs. It cannot wobble from leg to leg because there is only one plane on which it settles. Okay? Even if the floor is not perfectly level, it might not stand level, but at least it will stand stable. In fact, when dairy barns had dirt floors, milking stools were three-legged for this very reason. Okay? There you have it. If this was helpful, please leave a like and a comment and subscribe and all that good YouTube stuff, and we'll be back with the next section next week.